Course 3, Lesson 108, we are looking at similar solids. Hopefully this is just a quick reminder of what we do with similar figures, whether that's two-dimensional like we've looked at, or three-dimensional like we're going to look at today. So your goal for this, you'll be able to explore the relationships between measures of similar solids and then use those relationships to solve word problems involving similar solids. So we're not only looking at those similar figures, but using our relationships between perimeter scale factor, area scale factor, and volume scale factor. So what are similar figures? Remember, if I were to just look at a two-dimensional figure, let's say if I were to have a square, or let's say just a rectangle here, that's 2 by 3, I could say that I have a similar one that maybe is half the size, so 1 and 1.5. The reason that these are similar is because I have a scale factor from one to the other that is consistent between all of the sides. So let's see, which of these are similar figures? Well, it looks like if I were to take this big one to the smaller one, the corresponding side, 6 to 3, I would take half of it, multiply by half. Well, if that stays consistent with my diameter here, then I could say it's similar. And it does. It looks like I have half of that amount. Remember, sometimes it's hard to see some of these relationships. This one was easy. But if you get stuck, if you're trying to go from one to the other, big to small, then I can look at this relationship of 3 to 6, giving me my relationship of 1/2. Okay, and same with that 4 over 8 is actually the same. So let's see if it's the same here. If I'm going from big to small, is 3/4 equivalent to this relationship here, 4 over 8? And we would say, no, those are not equivalent. 3/4 is not equivalent to 1/2. This relationship of 3/4 is not equivalent to 1/2. So these are not similar figures. Well, the first one is. So we're looking for that same scale factor between all of the side lengths. So just to review, the relationship between scale factor of our dimensions, basically our perimeter, our area, and our volume. If we have this scale factor for our perimeter, I often show it as perimeter scale factor. It's just our scale factor. But when we go to our area scale factor, we are going to square it, scale factor squared. And then when we go to our volume scale factor, I say I'm going to take that original scale factor, this one up here, and cube it. We've looked at that in many lessons so far. So let's put it into practice. An architect builds a scaled model of a building she is designing. The scale model is 1 inch to 5 feet. So what is the scale factor from the model to the building? Well, we would want to say, oh, it's just times 5. 1 inch times 5 equals 5 feet. And we would be wrong because this little reminder below says scale factor must be in the same type of measurement, which means I need to be in all inches or all feet for this. And I would say probably turning this 5 feet into inches is going to be easiest. So we can do that really quick here by saying 5 feet over 1, using our skills from before to get rid of these feet, turn it into inches. Well, 1 foot is 12 inches, so I multiply across and get 60 inches. So I actually have a relationship of 1 inch to 60 inches, meaning my scale factor, my perimeter scale factor, one-dimensional, is times 60. Okay, and we don't actually have to show that times. We assume that it's there. So if that is true for the perimeter scale factor, what if I talked about the surface area? So area scale factor. Well, based on what we've learned in other lessons, how many times is that surface area compared to the original? Well, we would do 60 squared, which you can multiply that out. It should be 3,600. And so that is our scale factor. It's 3,600 times bigger than the actual model. And then we go to the volume scale factor. I'm not going to multiply this one out, but I would say from that original scale factor of 60, I'm going to cube it to get there. We should, and I can probably do this, 216,000, I believe. Okay, it's much, much bigger for the real thing compared to the small model. Much, much bigger. Okay, so we're using that relationship between perimeter scale factor, area scale factor, and volume scale factor to move between all of these different measurements. But we have to start with it in the same units. Big thing, big thing. All right, an ancient artist was creating a cast bronze sculpture. If the artist wanted to create a similar solid bronze figure 10 times larger than the original, how many times as much bronze would be used? Well, think about this figure, whatever it might be, and we have it 10 times bigger, okay, from this original to this new, 10 times bigger, but that's just side length, so going from 1 to 10, or whatever it might be. So I can say my perimeter scale factor is 10. So if I were just looking at, if I were to outline this in something, I would need 10 times as much paint, or whatever it might be. But if I want to know maybe area scale factor, if I were to, I don't know, paint it, I would be doing 10 squared or 100. But since I'm talking about the figure, the actual sculpture, which is talking about volume, I'm going to take 10 and cube it to get, I need 1,000 times more bronze for the new figure, the bigger figure, compared to the smaller. Since they are similar, we can assume that this is correct. All right, the two cylinders are similar. If the lateral surface area of the smaller cylinder is 20 pi inches squared, what is the lateral surface area of the larger cylinder? A little bit of a different question here because we're given surface area when normally we're asked to find it or something like that. We don't have enough information to actually, well, we could work backwards and find it, but we don't need to. All we really need to find is what is the scale factor? And I'm actually going to reverse what we would normally do and say I want from smaller to bigger, what is that scale factor? Which we can definitely find by doing 3/2 or saying it's times 1.5. Which means if that perimeter scale factor, the actual lengths of this is times 1.5, then the area scale factor must be the square of that 1.5 squared, which is 2.25. So if I wanted to find the surface area of this other one, I would take 20 pi and multiply it by 2.25 in order to get there. And you can do that for yourself. 20 pi times 2.25 is going to give you your new lateral surface area. So you can go ahead, pause the video and try that for yourself. But that's what we're doing. We can kind of work backwards and use our scale factors to find more information. And close to the last one, I think second to last problem here. Yep. So the volume of a model car built to a 1 to 20 scale is what fraction of the volume of the car? What they're saying is that this 1 to 20 scale is the perimeter scale factor scale. But we want to be careful here. What I'm going to say is maybe this has a side length of 1 inch. So for the ratio to be true, I would say this is 20 inches. Well, going from 20 to 1, I must have taken 1/20th of the amount. But that's perimeter scale factor, 1/20th. That's the scale that we're using, 1 to 20. But we want volume. So I can skip over area scale factor, you can definitely find it, but we can also just go to volume scale factor to say if this one is a certain volume, then it is what fraction, or this one is, the small one is what fraction of the big one, or if I were to take the big one, use that fraction, I would get the small one. Regardless of how you look at it, we are still going to use that relationship of 1/20th cubed to get that volume scale factor. Which when you multiply it all out, 1 cubed is just 1. 20 cubed, let's see, that's 8 with 3 zeros. 1/8000th of that volume. So if this one is 8,000 inches cubed, if I wanted to know the volume of this other one, I would take 1/8000th of it and find that this is 1 inch cubed. Okay? So we can use these scale factors in order to find a lot of information. Still comes down to that relationship between the two. Last one, hopefully you can do this on your own by now, but I'll just show it once more. Toy doll model after an infant is 1 to 3 scale model. So if some dimension on this doll is 1 inch, then the actual baby would be 3 inches in that dimension. So the amount of material required to clothe the doll is about what fraction of the amount of material needed to clothe an infant. Well, if we're talking about clothing, we're not talking about a one-dimensional something. We're talking about 2 dimensions, so surface area. So I need to go and find my perimeter scale factor in order to find my area scale factor and find that fraction. Well, going from baby to that the doll, I would say I take a third. That's the relationship, 1 to 3. 1/3. That's perimeter scale factor. So when I go to the area scale factor, I would square that and get 1/9. So whatever the baby is wearing, 1/9 of it would be needed for that doll. Well, hopefully you see the relationship between all of these scale factors a little bit better now, along with being able to decipher if something is actually a similar solid and using those scale factors in context. I hope this helps with your homework and for studying.